Okay, let's just dive right into an absolutely crucial concept for any network engineer. Quality of service, or QoS. We're talking about how to actually cure the utter chaos of congested networks. Look, if you've ever had a VoIP call break up into those robotic stutters while someone else in the office was downloading a massive file, well, you've experienced the exact problem QoS is designed to solve. In this explainer, we're going to look at the tools we use to tame that exact traffic jam.
So, here's our roadmap for today. We're going to cover the network traffic jam itself, how to identify the traffic, queuing and scheduling rules, preventing congestion, and finally, Cisco QoS configuration.
All right, Section 1. The network traffic jam. Best effort versus VIP treatment. To really appreciate QoS, we first have to look at what networks actually do by default and why that causes such a massive headache. By default, IP networks use what's called best effort delivery. Essentially, the network tries its absolute hardest to deliver all your packets, but, and this is a big but, it makes zero guarantees. Best effort literally treats a massive file download and a delicate real-time voice call exactly the same. If the link is congested, they both just wait in the exact same line. Quality of service, though, it changes the game entirely. Think of it like a bouncer at an exclusive club. It creates differentiated services, setting up a VIP line so that critical traffic, like your VoIP call, gets guaranteed priority and bandwidths even when the rest of the network is completely saturated.
Now you might be wondering, why exactly are our VIPs so incredibly demanding? Well, it all comes down to the metrics we're managing. Bandwidth is just your raw throughput. That's what video streaming absolutely craves. But then look at latency, which is the delay from source to destination, and jitter, which is the variation in that delay. A file download, it absolutely does not care about jitter. It can arrive in staggered chunks, reassemble later, and you literally never know the difference. But a VoIP call? No way. It cannot tolerate latency, jitter, or packet loss. If those packets don't arrive in a smooth, steady, immediate stream, your conversation just becomes entirely unusable.
So, how do we actually engineer a solution for this? Well, historically, we had two models. On the left, we've got int_serve, which uses a protocol called RSVP to reserve resources end-to-end for every single flow. It's incredibly precise, but just think about the math for a second. A router would have to track every individual conversation. It scales terribly. And that is exactly why engineers usually rely on the diffserve model over on the right. Diffserve doesn't bother tracking individual flows. Instead, it groups traffic into broad classes, like voice or critical data. This is highly scalable, and it's the absolute standard in enterprise and service provider networks today.
Moving on to Section 2. Identifying the traffic. Checking IDs at the door.
Okay, before the router can actually prioritize a packet, it has to look at its ID and figure out what kind of traffic it is. Classification is always step one. And we can check IDs at different levels of the network stack, right? Down at layer 3, we can use access control lists to match source and destination IPs or protocols. Bump it up to layer 4 and we're looking at port numbers. For example, we might grab anything on port 5060, which is standard for SIP and VoIP. But let's be real, modern apps are sneaky. They use dynamic ports, or they just hide the whole shebang inside standard port 80 or 443. That is exactly where layer 7 deep packet inspection comes in, using Cisco's NBAR. NBAR actually looks at the application's signature itself, so it can recognize apps like Zoom or Netflix, completely regardless of the port they happen to be using.
So the really crucial point here is that once we've classified the traffic, we have to mark it so that downstream routers don't have to do all that heavy lifting all over again. We do this by stamping the IP header with a 6-bit DSCP value. And industry standards dictate specific tags for this. Expedited forwarding, or EF46, is basically the golden ticket for voice. AF41 is typically used for video, AF21 is for business-critical data, and way down at the bottom, CS0 is your best effort general admission line for regular everyday internet traffic.
But wait, here is a massive caveat. You cannot trust everyone. We absolutely have to establish trust boundaries at the edge of the network. Think about it. If we just accepted any DSCP tag that came our way, every single PC in the office could maliciously or even accidentally label its own general web browsing as EF. Your voice queues would get totally overwhelmed by YouTube videos. So the trust boundary is typically set at the first managed access switch. Basically, unless the device is something we strictly control, like a Cisco IP phone, the switch is going to strip away the user's markings and remark the traffic according to our strict network policies.
All right, let's hit Section 3, queuing and scheduling rules, managing the VIP lines.
Okay, so now that our packets have their VIP wristbands on, how do we organize the actual lines when the network inevitably gets congested?
Well, without QoS, the default is FIFO, first in, first out. Packets are transmitted exactly in the order they arrive. But, as you can probably guess from our earlier best effort discussion, putting our VIP voice packets at the very back of a line behind a massive file download is a surefire recipe for dropped calls and terrible jitter. I mean, FIFO works totally fine if the link is completely empty, but it completely breaks down the second congestion occurs.
So early attempts to fix this problem gave us priority queuing. Now, this method uses 4 strict queues: high, medium, normal, and low. And the rule is super simple. The router always empties the high queue before it even glances at the medium queue. It guarantees low latency, which sounds amazing, right? But priority queuing actually swung the pendulum way too far. If that high queue is constantly full, the lower priority traffic never ever gets transmitted. We call this starvation, and it can essentially break the rest of your network. To solve that starvation problem, we got CBWFQ, or class-based weighted fair queuing. And this is a massive step up. Instead of a rigid top-down hierarchy, the administrator defines traffic classes and guarantees a minimum bandwidth slice of the pie to each one. Maybe video gets 2 megabits, while critical data gets 1 megabit. Because every single class gets its own queue and its own guaranteed slice, nobody gets starved out. It brilliantly brings fairness back to the network while still actually honoring your priorities.
But our ultimate solution, that's LLQ, or low latency queuing. Now, CBFQ is great and all, but VoIP needs an absolute immediate green light, not just a guaranteed slice of bandwidth. So LLQ takes the fairness of CBFQ and adds a strict priority queue right on top of it. Voice and video go into this LLQ and are always serviced first. But to prevent that nasty starvation we talked about, this VIP queue is actively policed, so it just can't overstep its bounds. It really is the absolute gold standard for enterprise networks today.
Which brings us to Section 4, Preventing Network Congestion, Crowd Control Mechanisms. So, queues handle the lines, sure, but we also need crowd control to prevent the interfaces from getting overwhelmed in the very first place. When a queue fills up entirely, the simplest response is tail drop, meaning new packets arriving at the tail end of the line are just discarded. But this causes a total nightmare scenario called TCP global synchronization. Because TCP naturally backs off when packets drop, tail drop causes all your network flows to slow down simultaneously, creating this incredibly wasteful wave of congestion and idle time. So instead of suffering from tail drop, we use WRED, or Weighted Random Early Detection. WRED proactively and randomly drops lower priority packets before the queue is full. This breaks up that whole synchronization issue and keeps your overall throughput remarkably smooth.
We also have to decide what we're going to do with sudden massive bursts of traffic. And here we have 2 very distinct tools. Policing is just ruthless. It enforces a strict rate limit, and literally any packet that exceeds the limit is immediately dropped or demoted to a lower DSCP class, zero buffering. Shaping, over on the right, is far more polite. Instead of just dropping excess traffic, shaping buffers it into memory and transmits it later, creating a nice, smooth, steady outbound stream. You'll actually often see shaping used when you need to send traffic into an ISP's rate-limited circuit without triggering their harsh policing drops.
And finally, Section 5, Cisco QoS Configuration, Writing the Rulebook. All right, let's bring all this theory into the real world and see exactly how you'd write the rulebook on a Cisco router. Cisco uses a brilliant modular framework called MQC, and it maps perfectly to the journey we've just been on. It's a simple 3-step process. First, we define class maps to actually identify the traffic. Second, we define policy maps to tell the router what actions to take on those classes. And third, we just apply that policy map to the interface door.
So step 1 is the class map. This is where we literally type out the conditions. We'd create a class map named voice, and inside that map, we use the command match DSCP-EF. This is exactly where the router looks at the IP header and captures those VIP voice packets we talked about earlier. And we would do the exact same thing to isolate our video and critical data classes as well.
Then in step 2, the policy map links those classes to actual queuing actions. Let's say we name on policy map WAN QoS. Under the voice class, we use the keyword priority and assign 512 kilobits. That single word, priority, creates our low latency queue, our VIP fast lane. For the video class, we use the word bandwidth and assign 2048 kilobits. That creates our class-based weighted fair queue, guaranteeing it a 2 megabit slice of the pie, but crucially, without letting it jump the line ahead of voice.
Finally, step 3. We go to our interface, let's say serial 0/0/0, and we apply it using the command service policy outbound WAN QoS. We almost always apply QoS outbound because, frankly, that is where the congestion and queuing naturally occur as packets are leaving the router. And crucially, we always verify our work. The command show policy map interface is going to be your absolute best friend here. It shows you exactly how many packets are hitting each class, your current queue depth, and most importantly, if any drops are actually happening to your VIPs.
So, we've seen how QoS brings order to chaos, taking us from the high-level theory of diff-serve all the way down to the exact command lines in Cisco's MQC. But you know, networks are always evolving. So, I want to leave you with this provocative thought. Deep packet inspection engines like NBAR completely rely on seeing application signatures. As more and more of the internet shifts to heavily encrypted, disguised traffic, hiding in standard web ports, how will tomorrow's routers even know who the VIPs are? Thanks for joining me on this explainer, and keep questioning the network.